Hello, everyone. Welcome back. Today, I'm going to be talking about the graphs of reciprocal functions. So let's get started. It says here, given that y equals f of x, the reciprocal is y equals 1 over f of x. So long story short, when we see a function in the denominator, then that's called a reciprocal function. The x-intercepts of the original function are the vertical asymptotes of the reciprocal function. A reciprocal function of linear and quadratic functions has a horizontal asymptote of x equals to 0. Intervals of increase on the original function are intervals of decrease on the reciprocal function and vice versa. If the original function has a local min at point x equals a, the reciprocal function will have a local max at x equals a. All the y-coordinates of a reciprocal function are the reciprocals of the y-coordinates of the original function. So what we're going to do is we're going to do some examples where we talk about reciprocal functions. We're going to draw the original, and we're also going to sketch the reciprocal of that original using some of these key points. So we'll be going back and referring to this list quite frequently today to get there. All right, so for the first one, it says, given the function y equals negative 2x minus 4, determine the asymptotes, intervals of increase and decrease, and min and max of the reciprocal function, and sketch the function. So before I do any of that, I'm actually going to sketch the original function first. So what would the original function look like? Well, the original function is just a line, right? We start here at negative 4, and then negative 2 is our slope, so it's going to look like this. So here's going to be our line, like that. There we go. So that's the original function. So what did the guidelines say about the original function versus reciprocal function? So the first thing it said was the x-intercepts of the original function are the vertical asymptotes of the reciprocal function. Okay, so when it says determine the asymptotes, that key is going to help. So what are the x-intercepts of the original function, or in other words, the zeros of the original function? Well, looks like at x equals minus 2, we have a 0. So that means that the asymptote of the reciprocal function would be, x equals 2. So our asymptote, so for asymptotes, we would have a vertical asymptote at x is equal to negative 2, right? Because we have a 0 there, or an x-intercept on our original function. So that means that that's where we have our, our x-intercept, or our vertical asymptote for the new function. Okay, now that's the only one, so we can move on to the next point. It says a reciprocal of a linear and quadratic function has a horizontal asymptote of y equals 0. So the original is a linear, right, which means it is linear or quadratic. It's one of those, it's linear. So therefore, yes, we do have a horizontal asymptote at y equals to 0. Then it says intervals of increase on the original function are intervals of decrease on the reciprocal and vice versa. So what does that mean? Well, on this entire function, it's always decreasing, right? It's always decreasing all throughout. So that means that on the new function, it's always going to be increasing, right? Because the interval of decrease on our original is just the whole thing. That whole line is always decreasing. So therefore, the reciprocal is always increasing. So I'm going to say intervals of increase for the new function for the reciprocal would be everything from negative infinity up to infinity. And then as for intervals of decrease, there would be none, right? Because on our original, it was always decreasing. So therefore, on our new function, it's always increasing. So there's no intervals of decrease on our new function. Okay, Then it says if the original function has a local min at point x equals a, the reciprocal will have a local max at x equals a. So this doesn't really apply here because we don't really have any specific local mins or global mins or global maximums or local maximums or anything like that. Here it's just a line, so we can skip that one. Then it says all y coordinates of a reciprocal function are the reciprocals of the y coordinates of the original function. So what does that mean? Well, that means we can find a couple points when we actually go to sketch it. Is long story short what that means. All right, but now I think we have enough information to figure it out. So it says, it did say determine the asymptotes, the intervals of increase and decrease, and the min slash max of the reciprocal function. Well, there is no really min slash max because for that we would have to have like, minimums or maximums on our original. So therefore, there's no min slash max. So I do want to write just a quick statement about that because it was something asked for, and that way when someone goes to look at this, they don't think, oh, maybe we just forgot to write about that. We know we didn't forget. It's just that there are none. Okay. So now I'm going to erase the original function and I'm going to draw the new function. So first off, let's draw a vertical asymptote at x equals to -2, like that. And then a horizontal asymptote at y equals to 0. And I'm going to label those. We have a vertical asymptote at x equals -2 and a horizontal asymptote at y equals to 0, like that. And then the function is always increasing and there's no minimum or maximum. Now we're going to actually use something that we hadn't used previously, which is this last point here that says all the y coordinates of a reciprocal function are the reciprocals of the y coordinates in the original function. So let's see. Let's see what that means. So at -3 on our original function, what would we get, right? If we plugged into our original function, y equals -2 times 3 minus 4, that would be -10. So that means that 1 over 10 would be the answer for our new function, right? 1 over 10. What about -1? What about -1? Oh no, I've done this incorrectly. My apologies. I looked at 3. I meant to look at -3. So this should actually be 6 minus 4, which is 2. Okay. So that means that at x equals to -3 on our original function, we would get 2. So therefore, we would get a half on the new function. So here we would have -3 and then a half as a point. So that tells us that the first part of this reciprocal function is over here, right? Because I wasn't sure if it was here or if it was here or if it was here or here, right? We weren't sure. Now, given that we chose -3, it would have to either be this quadrant here, quadrant 2, or quadrant 3, and we found out that it was indeed quadrant 2. So that means the other one should be the opposite to that, right? If we just think about our what's it called, our parent function for this type of question, right? So let's see what it is though. Let's get the exact point. So on our original, if we have x equals -1, what will we get? We'll get y equals -2 times -1 minus 4, which is 2 minus 4, which is -2. So that means the reciprocal of -2 is what? It's -1/2. So it's going to be here like this. And then we'll just draw that. And there we go. So, long story short, by using what we know, by using these steps, by kind of going through each of these steps one by one, we're able to figure out from things about the original function, we're able to find out things about our new function and then apply them and then use it to graph. And that's great. Okay, let's move on to example 2. It says, given the function y equals x minus 4 squared, determine the asymptotes, intervals of increase and decrease, and minimum and maximum of the reciprocal function, and sketch the reciprocal function. Okay, so here's what I'm going to do first. I'm going to sketch the original function, because that will help us determine things about the new function. And actually, this time I'm going to write down stuff for f of x, right, for our original function and for our reciprocal function as well. Okay, so let's do that. Let's do that. So for our original function, this is x minus 4 squared, and the negative 4 there, it's inside our brackets. So it's going to look something like this, our original function. And it's going to go over 1 up 1, over 2 up 4, so just a regular quadratic pattern. So far, all I've done is I've just graphed the wrong thing, the thing we don't actually want, but just, just for argument's sake here. Okay, so let's have a section here that talks about f of x, and then a section over here that talks about 1 over f of x, which is essentially what we're trying to get. So the first thing it says is that x-intercepts on the original function are vertical asymptotes of the reciprocal function. So what are the x-intercepts of this function, or the zeros? Well, there's only one, and it's 4. So our x-intercepts is x equals to 4, which means that for the reciprocal function, that the asymptotes, that we have a vertical asymptote at x equals to 4, right? Because that's what it said. It said that if we have an x-intercept on our original, that means we have a vertical asymptote in that same place in our reciprocal, which makes sense, right? Because if our original function is 0 in that spot, in that place with respect to x, then we're going to end up once we flip it, right? Once we take our reciprocal, we're going to have an equation that has divided by 0, and that's not valid, right? It's not valid to have divided by 0. We just can't do that, right? Okay. Now, although that said, there are other types of discontinuities other than just asymptotes, but in this case for reciprocal functions, it does always mean it's an asymptote. We'll get into the other possibilities in future days, though. We won't tackle all of that today. Okay. Step 2 says the reciprocal of a linear and quadratic function has a horizontal asymptote of y equals 0. Well, this is a quadratic, so therefore we have a horizontal asymptote at y equals 0. So there we go. Okay. Number 3 says intervals of increase on the original function are intervals of decrease on the reciprocal and vice versa. Okay. So what are our intervals of increase on our original versus intervals of decrease? And then let's write those for here too. Okay. So our intervals of increase on our original, well, this function increases from 4 all the way up to infinity, right? So from 4 to infinity, we have an interval of increase, right? Now, what about intervals of decrease on our original? Well, from negative infinity all the way up to 4, we have an interval of decrease where it goes downwards. And we know what they said. They said that that the opposite is true for the reciprocal. That for the reciprocal, the interval of increase is actually the interval of decrease. So from 4 to infinity, the reciprocal will be decreasing. And as for negative infinity up to 4, that's the interval of increase on our reciprocal. So I switched them, right? I switched them because we're taking the reciprocal. Awesome. All right, and what does the next point say? The next point says if the original function has a local min at point x equals a, or this goes for global min as well, the reciprocal will have a local max at point x equals a. Okay, so in the original function, we have a minimum point at 4, 0, right? So here we have a min at the point 4, 0, which means that on our new function, we have a max point at 4, 0. Now there is a little trouble that we're running into with this one, which is that we already said that at x equals 4 we have an asymptote, and so 4 actually is not a valid number for this, and so we actually don't. So generally we would have max at 4 equals 0, but I'm going to say actually no, no min slash max, because the only point we would have that actually has a vertical asymptote. So we'll say because of vertical asymptote. Okay, so an asymptote always overrules anything else that would be there. Okay, because in this case we have to think about it of, well, just because there would be a local max or a global max or whatever it might be in other circumstances, we can't just overrule the fact that when we take the reciprocal of x minus 4 squared, subbing in 4 there is still going to get us 1 over 0, which is still invalid. Okay, and so the vertical asymptote overrides the rule about minimums and maximums. Okay, and then all the y coordinates of the reciprocal are the reciprocals of the y coordinates on the original functions. Okay, so let's go ahead and talk about that. So which points would we have here? So over here we have points 3, 1 and 5, 1 on our original. Now the reciprocal of 1 is just 1 over 1, which is still 1. So therefore on our new one, we also have the points 3, 1 and 5, 1, right? Because I did take the reciprocal of my y coordinates, which is 1, but the reciprocal of 1 is still 1, right? So I still did do something here, even though it does look like they're the same points, because, I mean, they are the same points, but we still did something is a key point I want to make sure we get across. Okay, so now let's do part B, which is to sketch this reciprocal function based on the information we know. So first I'm going to sketch the asymptote. So x is equal to 4. Oh, x equals 4. There we go. Okay, and then horizontal asymptote, y equals to 0. Okay, all right, and then let's go to the points next, actually. So we have 3, 1 and 5, 1. And then we have an interval of increase from negative infinity up to 4. So that means we're going to be going up this way and down that way, right? Because we're going to be increasing this whole time. And then after 4, we are decreasing the entire time, according to what we found out. And so this would be the sketch of the graph. And there we go. All right, let's do a few more examples. Example 3 says, given the following graph, determine the asymptotes, interval of increase and decrease, min slash max points, and the points of the reciprocal function, and then sketch the reciprocal function. Okay, so first things first, let's refer back to our list. It says x-intercepts on the original function are vertical asymptotes of the reciprocal function. So I see an x-intercept right here at negative 0.5, and so that means that there will be a vertical asymptote at x equals 0.5 for our reciprocal function. Okay, and that's the only one I see, so we can move on to the next thing. The next point says a reciprocal of a linear or quadratic function has a horizontal asymptote of y equals 0. Well, they didn't actually tell us explicitly that this is a linear function, but it is a line, and all lines are going to, linear functions or linear relations, they express lines, right? And this is a line, and so yes, this is a linear function, and we can conclude that we do have a horizontal asymptote of y is equal to 0. Or same thing, if this looked like a parabola, well, we could say, oh, well, there you go, that's a quadratic function, so therefore the same thing applies. Okay. The third one says intervals of increase on the original function are integrals of decrease on the reciprocal function and vice versa. So this entire function is increasing. It's a line with a positive slope, so it's always increasing. So that means the reciprocal is always decreasing. So our reciprocal is always decreasing, or we'll say is decreasing on negative infinity to infinity, which is everywhere. So it is always decreasing. because the original is always increasing all throughout, right? Lines, lines in linear function in general, either they're always increasing or they're always decreasing, except for the line that has a slope of zero. I guess it's neither increasing nor decreasing, but generally speaking, lines are only going to go in one direction. They're not going to flip the way quadratics will. If the original function has a local midpoint at x equals a, the reciprocal will have a local max at x equals a. While on our original, there are no minimums or maximums, so on our reciprocal, there's also no minimums or maximums, so we can skip that one and just write a quick note here saying that there are none. And then our last one says all the y coordinates of a reciprocal function are the reciprocals of the y coordinates of the original function. Okay, so what does that mean? What are some points we have in our original that we can maybe flip to get what we need to get for our new function? Well, I see a point here at 0, 1. 0, 1. I also see a point here at -2, -3. So what does that mean? Well, that means that we have a point of 0, 1 on our reciprocal, and also a point of -2, and then negative a third, right? Because I took the reciprocal of my y values. I took a reciprocal of 1, which got me 1, and I took a reciprocal of -3, which got me negative a third, okay? And this reciprocal thing, this is not to be confused with negative reciprocal. That's only for perpendicular lines. In this case, we're just doing reciprocal. We're not also adding a negative in the mix here. Okay, very good. All right, so let's draw a sketch of this function. So we have a vertical asymptote here. And then we have a horizontal asymptote at y equals to 0, like that. And what else do we have? Well, we have the points 0, 1. So we have a point here on our function. And what else do we have? Um, okay, what else do we have here? We have -2, negative a third. So we have something like that. Then let's draw this. And there we go. Okay. And then are the increasing and decreasing intervals making sense as well? Yes, it's decreasing everywhere, right? It's decreasing everywhere because on the original it's increasing everywhere. Well, except for our asymptote, and our asymptote it's, neither increasing nor decreasing. So I guess we could switch this technically to say um, you know, all the intervals but not on the asymptote. We could technically say this. Actually, this would be a little bit better than to just say everywhere, because technically it's neither increasing nor decreasing at the asymptote. At the asymptote, it is invalid, right? However, I would probably accept it if someone just said negative infinity up to infinity. I probably would just let that one go. But this is a little bit better. This is a little bit better. Okay, let's move on to example 4. So example 4, I know we did a quadratic for example 2, but this is the first quadratic that we've done where we have 2 zeros. So that's going to be interesting. It's going to be interesting. Awesome. Okay. So let's talk about the x-intercepts. This is one of those actually where I wish they gave us an equation, because it is hard to read just from this graph. It's hard to read exactly where these are, but there is a way to figure it out. We can use our quadratic pattern. So over 1 down 1, over 2 down 4, 1 2 3 4. Okay, so that's going to be a little bit more than 2. I mean, we can see that. But how far will that go if we have a quadratic, just the regular quadratic, and we're looking for when is it equal to 5? Okay, so let's do that. Let's talk about if we just have a regular quadratic and we want to know when is, because we know that if y is 4, x is 2. But what if y is 5? Then what is x? That would be root 5. So let's find that out. What is root 5? Root 5 is about 2.236, blah, blah, blah. Okay, so you know what? For today, we're just going to use 2.2. Okay, we're going to say this is around 2.2. All right, so on our original function, we have two zeros. We have one at 2.2 and one at negative 2.2. Okay, so because those are x-intercepts on our original, those are going to be our asymptotes on our new function. So we have vertical asymptotes at x equals negative 2.2 and y equals, or sorry, not y, x equals 2.2. My apologies. Okay, so the next point over here says a reciprocal of a linear quadratic has a horizontal asymptote of 0. Well, clearly this is a quadratic relation, and so I am going to include that y is equal to 0 is going to be our horizontal asymptote. Then our next part says that when we have an interval of increase on our original, that's an interval of decrease on our new function, and vice versa. So what are the intervals of increase versus decrease? Well, over here, it's increasing all the way up to 0, right? From negative infinity up to 0, it's increasing. So that means on our reciprocal, that would be an interval of decrease. So interval of decrease, oh, an interval of decrease, for our new function would be negative infinity up to 0. And then the interval of increase is 0 to infinity, because that's the interval of decrease on our original function, right? So it's flipped. It's flipped, right? Awesome. Okay. Now it says here we have a maximum right here at 5, right? At 0, 5. So that means that we're going to have a minimum at 0, 5 on our new function, right? Or I guess at the, not at 0, 5, sorry, 0, 1/5, right? Because when we take a point from our original function, with respect to y, we take the reciprocal. So the minimum would be 0, 1/5. And then that's pretty good. Okay. So now let's take what we've learned and let's plug it into here to graph a nice reciprocal function. So we have negative 2.2 and 2.2 as our asymptotes. So let's draw those in. Or we could just use the exact and say x is root 5, because that's the actual one. Negative root 5 over here. And then over here we have root 5. Okay, awesome. All right, and then we have a horizontal asymptote at y equals to 0. There we go. And then we have intervals of decrease from negative infinity to 0. So that means over here, we're decreasing like that, right? And then also over here, up until 0, up until this point, 0, 1/5, we're also decreasing. And then we switch to increasing. We increase all the way back up here. And then also on this entire interval, we must be increasing. So we've got to increase over here as well. So even though it kind of flipped, we're increasing, right? Now, technically, an even better way to say the intervals of decreasing would be to argue that it's going to be from negative infinity up to negative root 5, and then again from negative root 5, not including that value, up to 0, and then for intervals of increase, it'd be technically better to say from 0 to root 5 and from root 5 up to infinity. So that's even better, right? Including incorporating those asymptotes into this is even better. But that said, would I accept this as your answer? Yes, I would. Yes, I would. But I am going to leave you with the ones that are even better, even more accurate. So int of decrease, and then int of increase. There we go. All right, well, there's that one done. Let's do one more example. And how are we doing for time? It's getting kind of long. Okay, so this will be our last example for today, and we'll pick this up next day. Okay, here it says for the function f of x equals x squared minus 2x minus 8, sketch f of x and its reciprocal. Okay, so to sketch any quadratic graph, what do? We factor or we put it in vertex form, one of the two. Okay, so I'm going to factor this because this looks like an easy enough thing to just factor. What are two things that multiply to negative 8 and add up to negative 2? Well, negative 4 and positive 2, so x minus 4 times x plus 2. So that means we have 4 and negative 2 as our zeros. And then that means that the average of those zeros, right, is what? It's 1. And so 1 is going to be the x coordinate of our vertex. So what's the y coordinate of our vertex? Well, let's find out. F of 1 is going to be 1 squared minus 2 times 1 minus 8. And that's going to be equal to minus 9, which actually is below this grid. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's expand this a bit. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that works. And then here we have 4, and here we have 2, negative 2. I'm just going to kind of label the important points. And then what will this graph look like? It'll look kind of like this. There we go. Okay. I mean, it should be more symmetrical than that. Oh, I made a mistake. I put it at 0, negative 9. It should be at, my apologies, 1, negative 9. It doesn't just look a bit wonky because I drew it wrong, or, because my drawing was a bit silly. It's because I actually put the point in the wrong spot. It should be at 1, negative 9, not 0, negative 9, as I put it. So let's fix that up. There we go. Awesome. Okay. Still looks a bit wonky, but at least it's accurate now. I think just this part's kind of, let's make it look more like a, I still don't love that. But anyway, the drawing is not what's important here. The important part is, is that did we get it accurate? And we did. We did. Okay. So let's first talk about the first step to graphing one of these. It says that the x-intercepts of the original function are the vertical asymptotes of the reciprocal function. So what are the x-intercepts here, or the zeros? Well, they're 4 and negative 2. So that means in our new function, we have a vertical asymptote as 4 and a vertical asymptote as x equals to negative 2. Okay? And then what about a horizontal asymptote? We do indeed have a horizontal asymptote of y equals 0 because this is a quadratic function. We can tell that by looking at the graph, and we can also tell that just by looking at the function that it's clearly a quadratic in standard form. So that part's easy. Okay, next let's talk about intervals of increase versus decrease. Okay, so we know that intervals of decrease on our original, so anywhere from negative infinity up to negative 1, would be an interval of increase on our new function. Okay, so our interval of increase on our new function is the same as the interval of decrease on the other one, on our new And this time, actually, let's try and take into consideration the asymptote. So we know there's a vertical asymptote at x equals -2. So I'm going to say the intervals of increase on our new function would be from -infinity up to -2. And then again from -2 up to 1, right? Because 1 is where our interval of decrease stops on our original, which means that's where our interval of increase stops on our new function. Intervals of decrease are going to be the opposite of decrease, are going to be the opposite, where we have from 1 up to 4, right, is going to be an interval of increase on our original, so therefore an interval of decrease on our new function, and then also from 4 to infinity. So it's the same thing I was doing before, except this time I'm just kind of retroactively, I'm accounting for the fact that the places where we have asymptotes we're going to have to skip over, as those are no as those are not intervals of increase or decrease specifically. Those are just points, those are just places where the function isn't valid, where it doesn't have a valid domain, like there isn't any domain there. And so if there's no domain, then it can't be an interval of increase or decrease past that at all, because it's invalid there. It doesn't work there. Okay, now what about minimums or maximums? We have a minimum on our original function at 1, -9, so that means we have a maximum on our new function at 0 comma -1 over 9, right? Because when we can take the reciprocal of the of what? We can take the reciprocal of the y value when we're doing points from the original to points of the new. Okay, so now let's graph this new function. So we have vertical asymptote at x equals 4, so let's draw that in first, actually. And then we have -2. Like that. Okay, awesome. And then we have a maximum at 0, -1/9. Oh, and I forgot the other asymptote. Let's draw that. So we have one like that. And then we know that we're decreasing from -2 up to 1. Oh, no, I did this incorrectly. Sorry, I said 0, -1/9. It should be 1, -1/9. My apologies there. I was going to say that doesn't look right. That doesn't seem right, and that's why it isn't. So there we go. Then we have an interval of increase from -2 up to 1. So up to our maximum, we're increasing, and then after we're decreasing. So we have something that looks like that. And then over here, we are increasing, right? It says that we're increasing from here to here and decreasing from here to here. So it must be in these quadrants there. Oh, that shouldn't look like it kind of goes up a little bit. It should look as though it's approaching our asymptote. That looks a bit more accurate. Very good. All right. Well, good work, everyone. That is it for today. I hope this was a good introduction to graphing reciprocal functions, and I will see everybody next day. Bye, everyone.